Welcome to this presentation. My name is Mark Scythian. The date today is October 20th, 2025. So if you're working on a gas turbofan engine engineering or physics problem, such as this one, it's a very common one. You're asked to solve for these 6 computational solutions based on the information presented. So you may be studying for a physics exam or maybe a thermodynamics or even a turbomachinery exam. And this is a very common problem. So I'm going to present the solution if you stick with me for about 10 minutes here. So we can go over to the whiteboard. So we can start with the first inquiry of 6. And that is the total air mass flow rate. So if you quantify the m dot sub ch in the literature, that would be the core air mass flow followed by the m dot sub cc, which is the beta m dot sub ch, or the fan bypass cold airflow around the core, its mass airflow rate. Next, we have the total air mass flow rate, so that's m dot sub a is the sum of m dot sub ch plus m dot sub cc. So we can equal that to the quantity of 1 plus beta times the m dot sub ch. So what we're doing here practically is finding the energy balance on the core stream. So that is the product of m dot sub ch times the coefficient of pressure. So again, you have the gamma value C sub P over C sub V, but we're isolating just the C sub P, then times the quantity difference of the temperature, absolute temperature sub ch minus the absolute temperature sub A plus m dot sub cc times, again, the C sub P and then the product of the difference of T sub C from T sub A. So look those up in the periphery definitions, and then you can quantify the components in a more practical method. But if your instructor requires these, then make sure to commit these to the repetition. And so that just translates to the m dot sub f times the q sub r. So that is the flow rate with respect to the r value. So then we can substitute m sub c as is in the literature and then equate it just to the product of m dot sub f times q sub r. So what this means practically is just to plug in the values. If you go back to the problem and spend a little time on it, you'll get this value iteration. Then we can simplify it in this pattern here, or it's the same thing, but it's just reducing it down into a workable solution. So initially the m dot sub ch yields 403.6 kilograms per second. So we take that times 4 in the constant, and so we get 1614.4 kilograms per second. So I'm going to clear the solution, and then we can go to inquiry number 2. And that is the specific thrust. So we could divide the absolute temperature prime divided into the m dot sub a, and that just yields the ratio of 200,000 over 2018.0. So that's approximately 99.1 newtons per kilogram per second. And so the third inquiry is the propulsive efficiency. So this is the eta sub PR, the eta symbol for efficiency. So again, you can look that up in your formulations. I'm just posting this here for reference, but the point is to estimate the effective jet velocity V sub E using thrust. So if you derive that expression as T is equal to m dot sub A times V sub E, you can yield V sub E is equal to T divided into m dot sub A. So that's just the 200,000 divided into 2018. So the T value is approximately 99.1 meters per second. So then we can apply it into the eta sub PR propulsive efficiency equation. And then yield the approximate value of 4.61% for the propulsive efficiency inquiry number 3. All right, so we'll clear the solution, these two solutions, and go on to 4. 4 is the thermal efficiency eta sub TH, so that's just the thermal efficiency or the kinetic energy output divided by the fuel energy input. So what we get for usable energy divided into the total potential energy or the fuel energy input. So again, you can look this equation up and apply it. If it looks familiar, use it. So if we just solve for it algebraically, we can equate this answer here. So we start out initially with the eta sub TH or thermal efficiency equation. So this then yields a thermal efficiency of 2.30% for number 4. Now moving on to number 5. This is the overall efficiency eta aught or eta sub 0. So that's just the product of the thermal efficiency times the previously calculated eta sub PR. So we just multiply these out and we calculate for the overall efficiency 0.106%. And then lastly, we have the thrust specific fuel consumption, TSFC. So that's the type of fuel consumption rate that's used in propulsion engines with respect to gas turbines, unlike piston engines, which use the brake specific fuel consumption. So again, we'll apply m dot sub F over T, and this practically turns into 10 divided into 200,000. So we yield an answer of 5.00 times 10 to the negative 5th power kilograms per Newton second. So that ends the solution. Thank you for watching this lecture and have a great day.